Okay. Now, let me pick up again from the point where we left. 12:15. So we have about half an hour. You may see that titles in the schedule are actually very categoric, but I mean, somehow I had to fill the slots with the title, but I think the distribution is best done in the sense of expanding on the concept of radar. Then we can also devote much less time to interferometry and polarimetry. We don't need all that time. So bear with me as we complete the walk through the concept of radar and its operation. And then we will see interferometry and polarimetry, at least to the extent that we can, that it can be useful for someone who wants to use the data and not see the details of the system. So now let me show you the image that I source myself. Okay, so it's not working very well. Now we have a technical glitch on the laptop, after that on the equipment. Great. So be patient. One moment, I'm sorry for this. But it's not working. Okay, so this is the example that I wanted to make. The images here of better quality than the ugly JPEG that I showed you in the previous, in the Etna image. You see, this is also a volcano. It's a volcanic island off the coast of the southern coast of Africa. Even in this case, you may see that it does make sense. If you look at it does make visual sense. If you look at the amplitude image here, each of these pixels is the visual rendition of how much backscattered signal the system obtained from that specific location. First of all, there's no spectral, as I mentioned, there's no spectral information. Each pixel is extremely shallow. You only have the information about how much power bounced back, but nothing else. Nothing else except phase of the wave. If you look at the amplitude image, as I said, it makes sense to the human eye. You see there's the caldera of the volcano. So the volcano is a sort of a cone with a reverse cone on top, which is called the caldera, where the lava may flow out. Okay, we look at the image and it makes visual sense. I see the cone and I see the caldera. I can also see from spatial information, I can also visually distinguish the solid land from the sea, don't I? Yes, for sure, because the sea tends to be more homogeneous. So I don't know what white or gray or black means, but I can see from the spatial arrangement, from the spatial pattern, that this is an homogeneous area. Sorry. This is an homogeneous area. This is less so. So I assume this is the sea and this is the solid land. Does that make sense? Again, with this, we're leveraging spatial information. We don't care how much energy comes back from that specific pixel. We're just looking at the whole picture. We're looking at how pixels relate to each other, and we can tell, oh, great. I understood this is solid land and this is sea. This is an exception, because that's an area where the sea surface was particularly rough. As we will see shortly, whereas optical remote sensing is particularly sensitive to the chemical composition of the object, radar remote sensing is particularly sensitive to the shape of the object. I think I already mentioned this at the very beginning. If you were to make a very rough distinction between what type of information you can get from optical and what type of information you can get from radar remote sensing, then this is the basic rule of thumb. Material, shape and conductivity. And you see it here, you can tell the solid land from the sea, not because it's a different material, but because it has a different shape, okay? This is nearly flat. This is all but flat, okay? And this is a little bit less flat. Probably we have waves here. Okay, another important thing to notice here is that this area is generally bright. I already mentioned that the scenes, typical scenes in radar look like if they were illuminated from one side. And you can notice that here as well. So this side is bright, this side is dark. It's like it's in shadow, okay? It's like an optical acquisition where you have a light shooting in from one side, not from top. Okay, this is a generally bright area, but if I look at the individual pixel, I will notice that there are huge changes between one pixel and the next one. There are very bright and very dark pixels next to each other. But the length cover is the same. So the response is very different, but the length cover is the same. It's like a vegetation, okay? Why is that? This is a phenomenon which is called speckle noise, which is typical for radar data. Even in the presence of a land cover surface, land cover type, which is homogeneous across the pixels, you will get very different responses. And the individual pixel will not point you to one specific land cover type. It's not the individual pixel, it's the statistic. The reason why you can tell this is different from this is not because of the individual pixel, because the values here will likely be similar to the values of the dark pixels here. But still, you can tell this area from this area from the statistics. If you look at the histogram of this area, it will most likely be a spike on low values. Whereas if you take this area here, it will be more evenly distributed. What is the important takeaway from this very simple observation? Is the fact that when you work with radar data, you should not rely on the individual pixel, because the individual pixel is never a stable basis for interpretation. The radiometry of the individual pixel is not a good source of information. You generally look at statistics. Okay, and that's about amplitude. If you move to phase, it's a complete mess. Okay, so if you just look at it at a superficial level, so if you just look at the values here without interpreting them, you can confidently say, you can safely say it's random to me. Okay, it doesn't say anything useful. However, there is information hidden in this mess. You need to be able to read it, which is not easy if you do not create the correct conditions, as we will see with interferometry. One more note. So I will introduce the discussion of polarimetry as well. This is the so-called VV image. What does it mean, VV? VV stands for vertical, vertical, meaning that the system that generated this data set is polarimetric, so it can distinguish the orientation of the electrical field, a thing which is never done with optical systems. Remember what I said earlier before the accident. Optical systems do not look at the orientation of the electrical field because it starts random and it ends random, no point. In the case of radar, you take care of sending out the wave with a known polarization, which is V, vertical in this case, and then the antenna is designed to listen, in this case, to listen only to the vertical component of the returning wave. Why is that relevant? It is relevant because then you make a second measurement, which you can see here, which is VH. What is VH? It's a second measurement. I still shoot it out. I mean, I'm considering the same illumination, same illuminating impulse, so it's still vertical. But then what I'm measuring here to the right, is no longer the returning vertical component. It's a returning horizontal component. And in fact, the image is different. Spatial information is similar. Spatial information is similar. You look at the two images, and the spatial arrangement looks the same. Okay, so the spatial information has not changed, but the radiometric information did change. This distribution of values is different from this distribution of values, and specifically, this looks much stronger. It's much brighter. Why is that? This is VB. It's an orderly type of reflection. I shoot vertical, I get vertical. This is VH, also called cross-polarization. This type of reflection is associated with so-called polarization rotation. When does polarization rotation happen? When you have a particularly messy shape for your target. A plain surface like the sea or like bare, flat soil will not rotate polarization. You shoot vertical, you get vertical. But if you have vegetation with a complex shape, with branches and leaves and trunk and a lot of complicated shapes, for physical reasons, when a polarized wave reaches this arrangement, it will get multiple reflections, which will end up rotating the polarization. So you sense the horizontal component, and you find it's strong, because it's not being rebounced as it was, but it has been rotated because of the of the bouncing. So this is a hint of why we are interested in polarization. Why are we interested in designing systems that can distinguish, that can discriminate between vertically and horizontally oriented fields? Because of this, because this helps us. Typically, VH, for example, it's a basic fact in polarimetric remote sensing that VH reflection is associated with vegetation. When you see VH reflection, you say, okay, great. This is a clue that there is vegetation there. Okay. The residential, I'll get to that. Residential area also has a complex shape, but the fact is that when the waves bounce off a building, for example, So, I mean, if you're talking about particularly disorderly residential areas, I agree with you. But if you're talking about regular buildings, like you can model them as a wall and a smooth wall and a smooth surface in front of it, what you get is a mirror reflection and then a second mirror reflection, which will bounce back the field basically as it is. Does that make sense? So if you naturally a residential area, a cluster of buildings is complex in shape. But it's a different type of complexity with respect to vegetation. In what sense? In the sense that if you were to model a residential area in a very simple manner, this would be the model. And this model involves two so-called mirror reflections, which flip the polarization once, the first reflection, then flip it the second time, but it's still vertical. With vegetation, it's different because it's much more disorderly. So the single wave gets broken down and reflected in multiple times in different directions. So that's what makes the difference, basically. And one more thing, no, I'll discuss that later. Okay, so is this answer satisfactory, or then we can pick it up again in offline? Okay. Okay, now let's focus on amplitude. Yes, but I mean, we already discussed that. Let me move forward. So, yes, I get to you. Let me say a couple of things about this. I mean, we have, yes.
Sir, is it not that only for the vegetation, but it can be detected for rock pits under that sea level, for rocks, rough rock surfaces?
Yes, but not under the sea level in general.
So is it only for the vegetation?
No, it's not. I mean, it's not only for vegetation. It's for the shape of vegetation. So the basic point is that this type of reflection, rotating the polarization, is caused by complex, particularly complex shapes. And the epitome of particularly complex shape is generally vegetation. If you happen to have rocky surfaces which are vegetationless, so bare rock, but not smooth, but very rough, like the result of complex erosion processes or something. As far as the shape is complex at the scale of the wavelength, that's an important point, then you will get a similar response, a similar situation. Another case which causes rotation of polarization, for example, is cracks in ice shelves. So if you have a solid volume of ice, then that's typical mirror-like reflection, won't rotate polarization. But if the ice is cracked, then you do have a complex shape. It's a crack, and the wave will enter the crack and will get reflected from the crack. But the shape of the crack is so complex that typically what you get as a reflection from the crack is rotated in polarization. Okay, does that make sense? So it's the shape. The fact is that most commonly, the most common case where you see enhanced cross polarization is associated with vegetation, because that's the most commonly found type of land cover that is capable of rotating polarization, but it's not the only one. I'm not saying that. Okay. Okay. So back to our yeah, this is an example of radar image. Oh, it doesn't work. I don't know why. No, it's my problem, not it's my laptop. When I say radar is sensitive to shape, this is an example. It's a Sentinel-1 data set that I downloaded from the Copernicus portal. It's on our hometown. And once more, like in the case of the sea, you see, this is the city, this is Pavia. And it's on the river which is called Ticino, which flows into the larger river, which is called the Po. One thing I wanted to point out here is that about shape, water tends to be typically dark, tend to appear dark in radar images because of its shape. Just like the sea, this is flat. It's completely flat. And flat areas typically backscatter very little. So they bounce back very little energy for the reason that we'll see shortly. So you will see them very dark, very low incoming power, very dark area. Cities tend to respond strongly because of this double bounce phenomenon. Vegetation depends on its shape, but you see, it's generally, this is VV. Okay, so we shouldn't expect vegetation to react too strongly. In fact, the rural area doesn't appear very bright, not as bright as the city, which activates this mechanism. But the other interesting point that I wanted to make here is about, for example, this is a bridge which goes across both of the rivers. And you see it's very reflective. It's very reflective. In fact, it appears very bright. This bright line here is the bridge. And it appears very bright because there's another factor involved in determining the amount of backscatter, and it's the so-called conductivity of the observed objects. We're talking about frequencies that can activate the motion of electrons, that can activate electrical currents in the illuminated objects. So if you have a metal object, which is the case for this bridge, then you will get a particularly strong response. Something similar happens, for example, for high voltage metal trellises, for other metal structures. They typically respond very strongly, not because of, how can I say, not because of their molecular structure, but because they are conductive, electrically conductive. Yeah. I think we can stop here for this presentation, and we can move on to the next. Are there any questions so far? Yeah. Yeah. Yeah, it's random. When you talk about phase, it can be considered random. So I only showed the amplitude for VH because showing the phase wouldn't have been very interesting, because you would see simply a second version of the same mass that you saw for VV. Because interpreting the phase is difficult. So I didn't think it was interesting here. Okay. Yeah. Now, let's move on to the next one, which enters a little bit into more detail into what the content of radar data can tell you if it comes up. This is increasingly troublesome. I don't know why. Okay, I will I will go quite quickly across this point because it's not, I don't think it's very interesting for you. What does radar data mean? Not that you're not interested in radar data, but in the precise physical meaning, because you need to really look into the details of the physical process. So I will limit myself to saying that in some sense, like for optical data, what you do is you identify for every pixel a corresponding portion of the Earth's surface to which you attribute the sensed wave that you're recording with the antenna. And you attribute to that surface a so-called radar cross-section, which is the unit of measure for the returning, for the reflectivity of the object. But since the radar technology and the science about radar was born in the surveillance domain, the idea of a radar cross-section was developed for an individual object observed in space, not for observing a surface, which is a need that came in later. So it was developed, this concept, about a single object, but not a surface. So when it moved to Earth observation, basically the concept had to be redesigned to adapt it to a surface. So they came up with this concept of density of radar cross-section. So taking the response of the hypothetical object and distributing it over a surface. I stop here. I mean, I don't think this is very interesting for you, but please remember that when someone talks about radar data and it's called density of radar cross-section, that's what they are talking about. And it's typically reported as sigma naught. Sigma naught. This is a standard denomination. So what is the content of the pixel? It's this sigma naught. What does it mean? Well, we should go into the details of the physics. So I would limit myself to say, okay, this is a numerical way of measuring how much backscatter you get from the observed area. Okay, and it's for unit surface. So we skip all the parts on the physics, and we go straight to the data itself and what causes a particular value for that variable. And so now here I report two images, so two visual renditions of two data sets that were acquired on the same area. And particularly, it's a dried up salt lake in South America. I think it's pretty well known among those who study these phenomena. It's a Salar de Uyuni, which is a salt surface. Basically, the water has gone, and you only have salt there. And if you look at it with an optical instrument, and then you generate a true color image out of it, you don't even need to bother doing it because you go to Google Earth, as I did, and you automatically get a true color rendition of the data set, and that's it. That's what I put here, okay? And you look at it and you see it's white. Well, no surprise, it's a salt surface. It's white as it is supposed to be. Whereas the rocks around are brown, various degrees of brown or green. Now, if we switch to optical, X-band optical, in this case, we see a completely different landscape. Spatial information still suggests, it's not the same, but still suggests that you're looking at the same place. See, the shape is reproduced there, not exactly because the viewpoint is different. There's a number of differences, but basically the spatial information, i.e. the shape, tells me that I'm looking at the same object, but from a very different perspective. The radiometry here is extremely different. The area, the Salt Lake area, which was so homogeneous in the first acquisition, becomes something severely inhomogeneous in the radar data set. Why was it homogeneous here? What's the reason why I look anywhere and I find the same answer? Same feedback from the area using multispectral data. Spectral signature, yes. Because why is the spectral signature the same? No. Yeah. 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 So if I look here, I find a certain spectral signature which translates into white in this image. And then I move to another location which is still salt, same spectral signature, same color. So it's not surprising. Obviously, it's homogeneous because it's all made of the same material. Optical data, material, same data. Except for errors, obviously, but same material, same data, minus the disturbance factors. If I switch to radar data, I'm looking at a very different aspect of the same thing. It's still salt, but look here, it's salt and it's salt, but the response is very different. Why is the response different? Sorry? Maybe it is also connected, yes, but this is band X, so its penetration capability is very limited. But I mean, I think it's this microphone's fault. Yeah. Okay. Test. Okay. Well, what causes this difference? Possibly, but especially shape. What is the difference? Probably it's a roughness. It's a shape difference. When you use this type of acquisition technique, you're not looking at the material. You cannot see the material in general. You can see the differences in shape. So something that you cannot see here, because it's the same material. So shape is largely ineffective in changing the response. But it becomes critical here, where probably you have a rougher surface here than here. Probably the salt water had more time to evaporate in one case, so it left a smoother surface rather than in the other case, or maybe the concentration was different, I don't know. But the fact is, my interpretation is this area, because I know how this data works, this area is rougher than this area, so it reflects more. The impact is given by the shape. The shape, which in this case is the surface shape. Note regarding the remark from your colleague that the shape, unlike optical data, we're having to do with much longer wavelengths here. Remember, it was microns or even nanometers in the optical case. With these wavelengths, the penetration capability is practically zero. When you use optical remote sensing, you're always looking at the surface of objects, except for transparent ones. So like if you're looking at water, obviously it's a different story. But if you're looking at objects that are opaque, like most of the time when you look down to the Earth, then you're looking at the surface. Whatever happens inside, you won't see it. With radar, the story is different because the wavelength is much longer. Centimeters, even decimeters, in some cases even meters. When you have wavelengths this long, they can penetrate into objects. So don't assume that when you see a reflected field, it was reflected by the surface alone. No, not necessarily. In many cases it is, but in many other cases, the wave will penetrate into the surface and it will generate backscatter even from the body of the object. So much so that in many cases, radar sensors are used for discovering buried structures. Many discoveries in archaeology were made thanks to radar. So the scientists knew where to search, but it was the radar that told them, look, there's something buried here. And this is something that you cannot do with optical remote sensing unless you use indirect indicators like the growth of stunted growth of plants, because there's something beneath, et cetera, et cetera. But you're not observing the object directly. You're observing the consequences of the object. Whereas in radar remote sensing, especially not in band X, not in band X. Band X is short, 3 centimeters. But if you look at band L, 1 meter, or band P, multiple meters, then that's something that can be done. You get a reflection from the buried objects. Okay. So now, in this part of the lecture, in the next part of the lecture, because now I see the clock, and as usual, now we had to recover some of the time lost due to the technical inconvenience, but I don't. Can you withstand me for 5 more minutes? Are we?
Yes, we can go up to 1:15.
At 1:15? Okay. So if it works for you, yeah, I would say let's go on. Are you sure you can manage it? Great. Okay. So we look into the target parameters that determine this backscattered field. I will fly pretty high above it because, I mean, if we go too much into detail, we don't have time, and I don't want you to get discouraged if you don't have experience with this. But okay, let me tell you one thing. That one fact that I only mentioned it very briefly, but it is very important in this context, is that the acquisition, for reasons that we will see shortly, the acquisition of radar data always happens from an oblique angle. Unlike optical data, you cannot stand on top of the observed object and look down, straight down at it. You need to look at it at an oblique angle. Why? Well, I will explain that, but for the time being, be aware of this fact. You look at it from an oblique angle, not like this, but like this. And this has an implication, an important implication, which is the fact that Since you're using monostatic, remember, we're using monostatic systems. So whatever location you find yourself in, whatever location the radar finds itself in, that's the starting point and also the arriving point of the measured wave. So that's the reason why we talk about backscattered field. Because what we measure is not whatever radiation leaves the surface, but just the portion which goes back in the same direction from where it was shooted originally. So, it was shot originally. So, if we are in a situation like the one illustrated here, where you have a perfectly flat surface, the physics tells you, I mean, I'm not going into the details, believe me, probably many of you know about this fact, but the others, please, I ask you to believe me. If you look at the physics of this phenomenon, the physics will tell you if it's a flat surface, when flat means that surface bumps are small compared with the wavelength, then the wave will be reflected mirror-like. So the wave, if you have a flat surface, like smartphone screen, it's very flat, then the reflection will be mirror-like, so much so that you should be able to see it on, no, not because it's too much illuminated. Can I switch off the lights for a moment? Please? No. Okay. Okay, so this is very flat, so you should be able to see the reflection. It's mirror-like, meaning that it basically conserves the angle very cleverly. The reflection angle equals the incidence angle in a very precise manner, because it's a physics fact. Okay, if I replace the smooth surface with a rough surface, and I do the same experiment, I notice that doesn't happen anymore. Why? Because the radiation gets scattered. Okay, so if the surface becomes rough, then I cause a number of displacements across the elementary elements of reflected waves, which tend to cancel each other. Well, let it be. It becomes scattering, meaning that the radiation is distributed across a range of different directions. Okay, I think we should switch it back on again, otherwise the recording may not be very good. Okay, thank you. Okay, so when I have a situation like this where delta H becomes comparable with the wavelength, then the radiation which used to bounce off in one direction starts being distributed everywhere, almost everywhere. So what happens is basically summarized here. Mirror reflection, very smooth mirror reflection, medium smooth, some mirror reflection, some scattering in different direction. When you have a very rough surface, then the diffusion becomes almost total. You cannot even tell from where the wave came in. Why is this relevant? So why did I take so much of your time to tell you this? Because this is very important for understanding radar data. Why? Because the amount of radiation which is diffused, which is scattered, determines your recorded backscattering. Let me try and make it clearer. If you are in this case, so if you have a smooth surface, or basically smooth surface, like the river in the image that we saw, it's very smooth. It's mirror reflected. So if the antenna is located here, it won't see any backscatter because all the energy is going to the opposite direction. Okay, No way. You won't see anything. You won't get any or almost any backscatter. So you will see a dark surface in the image that we will derive from the data set. If you have a moderately rough surface, so it will be some mirror reflection, but also some diffusion, some scattering. Part of it will go back to the antenna and will be recorded. A minor part. But if you have a very rough surface, so if the bumps are big compared to the wavelength, then it will be completely diffused, and this component will start becoming strong. You can summarize that in basically in this graph, where you have the incidence angle and then the amount of power that you would receive from a surface. And you will see that if you have a very smooth surface, in order for you to record a backscattered field, you need to have a very small incidence angle. So basically, you need to be shooting like this and then recording, then the ball bounces back, right? But if you have a smooth surface and you put yourself in this position, the ball bounces everywhere. Very quickly, as you move off the vertical direction, you won't be able to record anything. That's a smooth surface behavior. As the roughness increases, then this curve tends to level down, because if you scatter everywhere, then it doesn't matter anymore exactly where you are located, right? Okay. So this is a general fact, the general physics fact. The more the surface scatters, the more the surface throws radiation in all directions, the more I will get backscattered field. But the curve, well, actually, if you look at the curve, it doesn't seem so, in the sense that all the types of surface can reflect a lot or less, so depending on the incidence angle. Now, the next step is, yes, but spaceborne systems need to be designed in a way that they don't have all the full range of angles available. There are technical reasons for which you need to limit the incidence angle to a certain range, typically between 20 and 50 degrees. In this case, in this range of incidence angles, typically roughness relates with backscatter. So since you're limiting the incidence angle to a narrow region, so I cannot acquire like this, I cannot acquire like this. I will be acquiring most likely in an intermediate case, right? So in that intermediate case, typically what happens is that no surprises. If you have mirror reflection, you don't get anything, and you see the black river. If the surface becomes increasingly rough, I will get increasing returns. And this is a very important interpretation key for radar images, visual interpretation key for radar images. If you have, like in this case, the rougher the surface, the more you move from the plains to the mountain, this is northern Italy, from the plain to the mountains, you see increasing levels of backscatter. Let me show you another example which relates with what I said before. This is a case where dam break was monitored by satellite. And in this very unfortunate case, you see you had a dam whose basin is very well visible in satellite radar satellite data set because it's flat. And there are areas where there were already I think these were rice paddy fields, which when the plants are not grown yet, they're very flat, so they appear as dark spots here as well, because it's typical for water. So after the dam broke, you can see that the amount of water obviously decreased a lot, and downstreams, you can observe flooding. Again, why? Because of the mirror reflection, which is granted by smooth surface of water. Okay, well, I think we can skip some. These are just examples of rough surface. What do you mean rough surfaces? This is rough. This is rough. You should always keep in mind that rough or smooth depends on the wavelength. So whatever reference should be made to the wavelength that you are utilizing, and depending on the system, this can be very different from each other. Okay, and then there's the shape in a more general sense. I already discussed this, but there are other cases where you have smooth surfaces, and for example, if you have this is a so-called dihedral structure, right? So a situation like this where you have a building and a surface in front of it is very effective in bouncing back the wave, but not always. Not always. Because if the building is oriented like this, then you shoot a wave to it and you get backscatter. But if the orientation was like this, not really. Because your wave would bounce here, then bounce there, then go away. Okay, so it's not always for granted. In general, it happens, but this type of structure, which is called trihedral, is extremely more effective, because in this case, with this structure, it doesn't depend anymore on the direction, and wherever you may be illuminating it from, you will get a strong backscatter. So this is another example of how the shape of the observed object impacts the backscatter that you will record. So the shape of the object is extremely critical in determining the backscatter. This is one example. This is an old image, ERS from ERS-1 of the urban area of Berlin, the capital city of Germany. Buildings, generally, even if they are not oriented perfectly, as we said before, they still, statistically, there will be, in any city, there will be a number of buildings which are oriented in the right way, which will bounce back a lot of energy. So in general, urban areas will appear bright. These dark spots are airports, very flat. These dark spots are lakes, very flat, dark spots. Let me give you a more illustrative example. This image was acquired on southern US, Houston, Texas. This is the footprint of the image. And this is the so-called quick look of the image, very quick representation, 5 more minutes. Let me see what I can do with these 5 minutes. It's a coastal area. See, this is the city of Houston. This is not very good in quality, but you can still see from the quick look image here that there's a bright area, which is the city, okay? But there's also an urban area here on the island. Let's zoom on it. There you are. the image shows obviously the sea, which is dark because it's flat. Not all flat. What happens here? A boat, right, a ship. So these dots are ships. Ships are the side wall of the ship is a vertical wall against a horizontal surface, so double bounce, so very bright. Plus, they are frequently made of metal, so this adds to the reflectivity. But let's look at the urban area. Notice the very flat airport runway and the vegetation next to the airport runway. This is rougher, so it's brighter. Urban area. If you look at the direction, you can have an intuition of how these buildings are oriented. And you can see that they are more or less oriented as the direction of the satellite. So they cause strong backscatter. But if we move to a different region of the same image, I think this area here is particularly interesting. Why? Because it's, well, I don't think this area is very different from this area. In both cases, it's an orderly built urban area, but see how different is the reflectivity. See how bright this is and how darker comparatively this latter is. Why is that? Think again. There's less double bounce, that's correct, but why is there less double bounce? I would say you're on the right path, but it's not yet the right answer. I would retouch it by saying there's not less double bounce in absolute terms. There's less double bounce in the sense that no. Right. That's a point. The double bounce is there, but the result of the double bounce doesn't go in the right direction. Why? Because of the orientation. See, these buildings are oriented in the right way. This is the direction of the satellite, more or less. Okay? And these buildings, can you imagine these buildings are orderly built for walled buildings. So if they are oriented like this vertically, then there will be at least one of the walls which will face the satellite, more or less, not exactly, but still sufficiently so. And so this will cause the double bounce to go back directly to the satellite. In this case, in the lower part, that will be at an angle. So the wave will bounce on the ground, will bounce on the building, and it will go elsewhere. So there will be still a response because building is not all regular surface, everything. There will be always something causing a little bit of backscatter. But see the difference. See how much one is brighter than the other. Okay. And yeah, I would stop here now. Let me say, one last thing, because I think this could be interesting. Then I will get back to that image because I think it's particularly interesting. The trihedral the trihedral reflection is sometimes caused on purpose with suitable structures like this, which are made of metal, for purposes of calibrating the sensing system. Because if you build a structure like this made of metal with known measures, with known conductivity in a known place, then you can expect a known amount of backscatter from it. And so you can tune the reading of the system based on what you expect from such a structure. Okay. And then I think I will stop here. Thank you for staying with me, because I really noticed that you have been attentive basically up to the last minute. And this is something which I appreciated very much. So despite the inherent difficulty of this topic, especially for those who hear about radar data for the first time, I saw you were more or less all attentive, and that's something which, as I said, I thank you about. Okay. Thank you.